All right, looks like we got a good crowd here this morning. Thank you so much for joining this morning's office hours, debunking the IO myths of LLM training. If we go on to the next slide, I'm pleased to be joined this morning by our expert Subramanian and Kartik. Thank you so much, Kartik, for joining us.
It's my pleasure, Boone. This is very, very special for me. This is a topic very near my heart. So just by way of introduction, I'm the Global Vice President for Systems Engineering at VAST. So I run the entire global team for pre-sales for VAST. However, I'm a geek by heart, and I do spend a lot of time especially in the field of generative AI. So I've learned a lot of things in the last couple of years by doing very large-scale deployments with many customers. And I wanted to share some of my insights on what I've learned, especially in the world of large language model and some of the most I/O intensive pieces of it, which are basically checkpointing. So just a little bit of housekeeping here, and I'll hand back to Boone to describe how to ask questions. Go
Yeah,
ahead.
if you have any questions during the event, we want to keep this interactive, so please drop any questions in the Q&A box. You'll see that at the bottom of your screen. If we don't get to your question during the webinar, don't worry. We'll get the answer to the question afterwards, and we'll send it to you via email. And just a reminder, this webinar is being recorded, and the recording will be sent out to you as well at the close of the event. But yeah, without further ado, I'll hand it off to you, Carter.
All right, let's dive right into it, folks. So just a quick overview of what is this world that we're really walking into? What is generative AI, and how does it work, and how does that work with GPU systems, etc.? I'm hoping that all of you do have some background in the world of using neural networks, but just as a quick baseline, the core idea behind neural networks is there are types of problems which are very difficult to do with traditional machine learning techniques. And especially when it comes to unstructured data, such as images or video or text. And these are really complicated. A simple vision model, as I've depicted on the screen here, is, say, I show the picture of George Washington. And I have a network with nodes in it and multiple layers, as you can see. And by exposing this network to many, many pictures of George Washington and others, eventually it learns. And it basically is able to break out the features and then ultimately do recognition and say, that's George. I know who that is. So the basic process of training neural networks is you show it a lot of label data, as I have in the graphic below the main one, and it makes mistakes. Initially when you show it something, it has no idea what it is, so it takes a guess. And if that guess is wrong, then you calculate some mathematical functions to measure the error, and you do something called backpropagation. And you propagate the error back, and you adjust the weights of the nodes themselves, and then you try again. And you keep doing this over and over again till you get better and better at the answer. And then eventually you're accurately able to predict that when I show a picture of a dog, I'm able to identify that as a dog. So this is for vision problems. Text problems are particularly nasty because words don't just stand in isolation. Like if I use the phrase work to live and I use the phrase live to work, these have entirely different meanings. However, they use exactly the same words. So word order matters. Word position in a sentence matters. The sentence position in a paragraph matters. As a result, even though there are only about maybe 100,000 words in the English language, there are quadrillions of ways that you can actually put them together to form text. And this is what makes language models particularly hard to do. Language models, of course, are these days a more sophisticated version of the simple neural network that I've shown here. They're what I call attention networks, okay, also known as transformers. So if you hear those terms, that's what they mean. And they are, I'm not going to get into the details of how transformers work, but suffice it to say that they are basically what we call sequence models. They are able to, in its simplest form, predict the next bit in the sequence. That bit could be a word, it could be a character, it could be a genome base pair, it could be a protein amino acid, doesn't matter what the sequence is. You can train these models to deal with any kind of sequence, and they get very, very good at predicting what the next sequence is, given the ones that have already predicted before. This idea is enormously powerful. As you have all seen, there was an explosion in interest in these kind of models, and they call it generative because, as the name suggests, they generate. Okay, they create stuff which hasn't been input into them by basically stringing together what they already know with what the input is, which is the user's prompt or whatever the other kind of input there is. So these kind of models have been exceptionally successful. The most famous one being, of course, something like ChatGPT, which is based on a model called GPT, or generalized programmable transformer. And these have been extremely successful in the market today. Now, of course, everybody and their grandmother has a large language model. Meta has released Llama, and Google has Palm, and Gemini, and OpenAI has GPT variants, and there's literally hundreds and thousands of models on Hugging Face where you can get all this stuff. But the basic process in going through this is pretty similar. For training, you start with a lot of raw data of some kind, and then you process that and convert it to what's called tokens. What is a token? A token is basically, think about it in simplest terms as a word. In more precise terms, a token is typically 4 bytes. And a rough way that I remember it is 750 words is about 1,000 tokens, okay? So when you're inputting the data, maybe it's all of Wikipedia, or maybe it's all of Slashdot that you're or all of GitHub that you're putting in there. Then you break it up into smaller chunks called tokens, and the tokens are what are really fed into the system after they've gone through the data preparation to get rid of the stuff that you don't want to train on, okay? Once you're trained, then you go through and customize it by a process called fine-tuning. And then eventually you go into a phase called inference, where you actually use the model to respond to data it has never seen before. This, by the way, is where the rubber meets the road, but we're not going to talk much about it. And there are techniques around this, such as retrieval augmented generation. You may have heard terms like vector databases and vector embeddings and all that. That's kind of where that comes in. But this virtuous cycle of data preparation, training, fine-tuning, inference with RAG is basically what happens. But the core idea under training is you propagate the data forward through the network, and then you do back propagation to correct the errors you make in the prediction. And you keep doing this as you get better and better. Clearly, the more high-quality data that is, you're going to get better and better results. The more complex the networks are, in many cases, you can solve problems which are very complex with something like this. Although the current trend is to go towards smaller models and much larger sets of data and high-quality data. So to train this is no mean task. From an infrastructure standpoint, these models can be very large, hundreds of billions of parameters describing this model. In contrast, the vision models are considerably simpler. They typically have hundreds of millions of parameters. So literally 3 orders of magnitude difference between vision and text-based transformer models and now multimodal models. They're really big. Dealing with this means that many, many GPUs are going to be needed to do this. Now, why are GPUs even needed in the first place? Well, the key mathematical operations as you train, as you go forward and back, forward pass and backward pass, is matrix multiplication. And GPUs are very, very good at it. This is, enough said, GPUs are here to stay. And sometimes these models will take thousands of GPUs to train. The workloads are very interesting. See, while the model is being trained, there's very little I/O. The input data sets are just tokens. They could be just a few terabytes or a few tens of terabytes or something like that. The data preparation piece is much heavier. But when you finally filter it down and you create it to tokens to train the model, that's a relatively modest amount of storage. And the output for these things is really just the model itself. I will go through more detail as to what the size of the models is. But the key thing is that there's not really too much I/O. There's a little bit of reading that goes on and a little bit of writing that goes on. So one might say, okay, what's the big deal? Why is everybody worried about performance for these large language models? There's one notable exception. This is large language model checkpointing. And that is the core topic for today, is how do we really understand this, okay? Couple of other high-level things. a lot of the I/O in these environments tends to be heavy random reads. Now you can't prefetch a random read, so this is why Flash is pretty much the standard for what most of these architectures use for the underlying storage. Secondly, I/O sizes vary a lot. Now this is quite a bit different from traditional high-performance computing workloads, which tend to be large block sequential reads or writes, and the data sets are big. Here, there's lots of small, medium, large IOs. They're all over the place, but the key thing is they're random and they're very read intensive. And that's really the thing over here. And in some cases, people will use heavy use of techniques like memory map files also to do this. And that, again, it basically shows up at the storage as a flood of random small block IOs. And that, again, is another reason why Flash is usually used for something like this. And, I represent VAST, and this is certainly a good platform for that. Interestingly enough, I will not talk about VAST at all in this. This is all about how large language model training works and how checkpointing works, okay? These are throughput sensitive workloads, not so much latency sensitive, but they tend to be really, really big. We have production customers who run tens of thousands of GPUs in a single cluster, training enormously large jobs here. And we witnessed firsthand exactly how intense the IO workloads can be for this, especially during checkpointing. So over to checkpointing. What is checkpointing? Checkpointing is essentially saving the state, the running state of a workload with the intent of being able to restart it some later time. Now, I should distinguish this from, say, a snapshot of all the data on the file system. Sometimes people think, oh, if I just snapshot the data, if I take a snap, then haven't I saved the state? Well, not really, because this is not just the disk state, it's also the state in memory. So it's really snapshotting this memory state for GPUs and main memory that really constitutes a checkpoint. And this is not a new idea. High-performance computing workloads and MPI frameworks and HPC shops have been doing this forever. Because, you know what? Very simple reason. Things fail. As the old saying goes, hardware will eventually fail and software will eventually work. And when hardware fails, you don't want to toss out all the work that you've done. The length of time that these jobs train is sometimes staggering. We've seen jobs run for 6 months at a time continuously. Imagine, if you will, that many months in, you lose some critical hardware component, server fails, GPU server fails. Now, all of a sudden, you don't want to be faced with the prospect of having to restart everything you did. So we want to be able to recover the state back to something close to where the failure occurred. Hence, you basically checkpoint. So a 200 billion parameter training with, say, 1 trillion tokens, it's going to take a lot of time. It takes over a month to be able to do this with H100 class GPUs as well. So these kind of failure rates are inevitable. I'll show you some statistics from Alibaba, who published a very nice paper. I have a reference in the next slide, where they basically say that even for a modest cluster, only 56% of their jobs actually ran with no issues. And eventually, some kind of hardware or software issue led to failure. So this underscores the requirement to be able to do checkpoints. Now, failure isn't the only reason people do checkpoints. You also do checkpoints because sometimes, because of the complexity of these models, you need to go back a few steps because something isn't looking right. In slightly more technical terms, as you train the models, you look at something called a loss function. And loss function basically measures the difference between the prediction that's made and the actual ground truth. And the idea with training and continuing training is the loss function keeps decreasing. And as it decreases, you get better and better with your predictions. Now, to make sure that it's actually doing this, because what it really is a big minimization problem in a very, very large vector space. And what happens when you start to do something like that is that it can get caught up in a local minimum. And then what happens is you would do something else called a validation, which is you would test that model at any stage with external data. And if the validation loss starts to diverge from the training loss, you know something is wrong. So you go back a few steps and you change a few things and you restart the training. So you may need to go back a few hours or a day or 2 days sometimes, just to make sure that if something isn't going right, then you have a chance to go and correct it and then not lose all that work again. So checkpointing is absolutely crucial mainly because of this fact here, stuff fails. This is the chart from Alibaba. And as you can see, 56% actually run, 57% maybe. And there's a variety of things that can go wrong. Okay, all kinds of stuff. Errors, CUDA errors, memory access errors, things hang, network errors, ECC errors, all kinds of stuff can go south. And any of these would interrupt the training. And restarting this is extremely painful, and you lose a lot of time doing so. So you want to be able to not just checkpoint quickly, but you want to be able to restore back quickly. As you'll soon see, there is nothing like free lunch. Yeah, Boom? You have a question?
That actually may be relevant to this slide. Thanks for the question, Ned. Ned was asking what kind of stresses, challenges, and obstacles are IT professionals facing as it relates to securing critical data and protecting sensitive information, specifically, in the case of this webinar, we're discussing, LLM training, but just curious if this is kind of the stuff that people are kind of seeing, if these are kind of the challenges that IT pros are seeing as it relates to securing critical data and sensitive information.
So quick answer to the question is absolutely. Security, governance, model reproducibility, all of these are crucial. Audit capabilities, logging, information preservation, compliance, massively, massively important. I cannot do justice to it on this seminar. Maybe I will do another seminar where we go through the security aspects for this. And there's many, many things that you have to worry about, including things like data poisoning, making sure that no one messes with your initial raw data or changes something, and as well as how do you actually preserve the state of the data, the code, and the model in a way that it can reproduce it, say, 6 months or a year from now, if you are hauled up by a regulatory agency or something like that. Connected with this are many, many other concerns like multi-tenancy, et cetera. As I said, can't go into the details there. I could easily spend 2 hours talking about that, but totally agree. These are all top of mind for most IT people, and they struggle with this because people aren't really thinking this through yet. Everyone is jumping on the bandwagon and saying, just buy some GPUs and run some stuff, because that's what generative AI is. And no, there's actually a lot more to generative AI than just doing that. But certainly good call out. We'll certainly set up another webinar and we'll go through that. Okay. So, yeah. Anything else, Boom?
That's it.
Okay, so now let's actually get under the hood over here. And from here on, we're going to get pretty darn technical, okay? So how does large language model checkpointing really work? So as I mentioned earlier, large models have peculiar problems when it comes to getting trained in this kind of an environment. First of all, they're large. So what do I mean by large? The size of a model is basically 2 bytes per parameter in the model. So let's take a toy example. Let's look at GPT-3, a well-known model. This was the foundation for the initial ChatGPT that came out. That's a 175 billion parameter model. And this means that if I have 2 bytes per parameter, the model itself is, basically 350 gigabytes in size. And that may not seem like much, but keep in mind that to train, this has to fit in the GPU memory. Clearly, GPU's memory is not large enough to fit one of them because like even an H200 GPU has 141 gigabytes of memory. Too small to fit a 360 gigabyte model. And to be fair, there's a whole bunch of more memory space which is needed during runtime, and I'll speak a lot more about that as well. So model size exceeds the GPU VRAM, and therefore you need a strategy to be able to deal with it. Secondly, there's a lot of more state in here, intermediate calculations, which also have to be stored in memory. So actually, there's a multiplier of 7 on the initial size of the model. So it's actually 14 bytes per parameter that you actually have to preserve in GPU memory. This means that you have to be able to spread the model out across multiple GPUs. This is the reason why NVIDIA and a bunch of OEMs like HP and Supermicro and Dell bring out the so-called DGX or HGX architectures, which have 8 GPUs each, and these GPUs talk to each other through NVLink. So this is because you have to be able to distribute the model across multiple GPUs, and there's a heck of a lot of crosstalk. And therefore, you need extremely high bandwidth interconnects between these GPUs to be able to do that. This process of shorting the model out is called tensor model parallel. By the way, all of this is well-known work. There's a beautiful publication, which I've referenced in the article below. There's a deployment model called Megatron LM. This is joint research from NVIDIA, Microsoft, and Stanford University, who basically looked at how you practically train super large models like this. And they basically recommend that you parallelize in multiple dimensions. The first dimension is model parallelism, where you spread the model across, say, the GPUs and one single DGX or an HGX. The second parallelism is, now, even then, the pipeline is pretty deep. Like GPT-3 has a number of layers in GPT-3, it's around 90 layers. And you cannot cram that much of work on one single server. So what you do is you have multiple of these GPU servers, and you basically have them work together in concert, and you split the pipeline across these. So for example, if you look at the graphic that hopefully you can see my cursor, the graphic in the middle. So the one on the far right is tensor model parallel. The one in the middle is pipeline parallel. So some layers get done on one of the GPU servers, and they pipeline that to the next server, which has the other layers in this, and so on and so forth. And you basically spread both the pipeline and the model across a set of GPU servers. This group of GPU servers, HGXs or DGXs, is called a pipeline parallel group. Okay. The size of this group varies depending on the size of the model, et cetera, but whatever it is, once it's there, the pipeline parallel group contains both the entire model and the entire pipeline. So it's almost like a self-contained unit. And this is a crucial point here, okay? Keep in mind the actual GPU cluster may be a lot bigger because you need a lot more flops to throw at the problem to do this in a timely fashion. But the pipeline parallel group is that subset which actually contains both the model as well as the pipeline in here, okay? And then, of course, the third piece is a more common piece, which is parallelizing the data. So if I have a lot of data, I have a bunch of pipeline parallel groups, and each one takes a little bit of the data. If I have 16 of them, then I say, hey, you take 1/16, you take 1/16. They all do this in parallel. At the end of a certain set of iterations, they all communicate with each other, and they update each other in the model, and then the next bunch of iterations start. And this is how training proceeds, okay? Combination of these three parallelisms is what is crucial to be able to successfully train large language models. There are other models too, other than Megatron. We won't go into that, but by and large, what we've seen in our customer base is 90% of customers use Megatron. And there certainly are other techniques which are being looked at this point. Here's the crucial point. What really happens when you checkpoint? In a pipeline parallel group, like I said, you got the full pipeline and you got the full model. You need to save the state of memory, of GPU memory, for every single GPU in a pipeline parallel group. Not the entire cluster. Burn this into your consciousness. You're not going to checkpoint every single GPU in the cluster. So if I have 1,000 GPUs in the cluster, I am not checkpointing 1,000. I'm only checkpointing the ones in the pipeline parallel group over here. For something like GPT-3, and I'll show you how we get the optimizations. Tensor model parallel is typically chosen as 8 because I have 8 GPUs on a server, so I spread the model across 8 GPUs. Pipeline parallel is typically 16. Could be 8, could be 16. It's about the same. Now, so that's about, say, if I choose 16, that's 128 GPUs in a pipeline parallel group. I may train it in a total set of GPUs, which could be 1,000 GPUs or 2,000 GPUs, or how many ever GPUs you want. But the pipeline parallel group is what really needs to checkpoint, and that's the only thing that matters here, okay? Now, let me switch to a very a little model that I've built. It's an Excel-based model. It's nothing fancy. I'm not claiming any huge intellectual property rights on this one. It's basically stuff that I pieced together after doing research for almost a year and a half. This is being cross-validated by NVIDIA. I presented this at, actually Sven, my colleague, presented this at ISC in Hamburg, along with Glenn Lockwood from Azure. It has withstood the test of time. Every model I've ever been able to check has adhered to this. So let me take you through some of the details of this thing here, okay? So how does checkpointing work again? Every GPU basically writes out one file, which is basically its memory contents. So this is done as a sequential large block write, and it's a buffered write. Okay, so it goes from GPU memory to CPU, and then it writes out the whole thing, spits the whole thing out, and it creates a file. In the example I gave before, 8 tensor model parallel and 16 pipeline parallel, that's 128 GPUs. Each of these, every GPU will write out one file. So you'll have 128 files, and these constitute the entire checkpoint for that entire training cluster. Restoring, of course, is a different question, because now you're going to restore not just to that pipeline group, but to all pipeline groups. The reason you don't checkpoint all pipeline groups is because they're all identical to any one of them, so you only checkpoint one. But restoring, you're going to have to restore everything. So the performance you need for restoring is actually typically a lot higher than what you need, but it's all read. Checkpoints are 100% large block sequential writes, which are buffered. And each GPU basically runs one thread against this, okay? So often what people will say is, I want checkpoints to occur within a certain time frame. Now, why is that? That's because checkpointing in Megatron is a synchronous process. What I mean by that is, when the model is checkpointing, training pauses. And it pauses until the checkpoint is finished, and then it resumes. So clearly, you don't want the checkpoints to take a huge amount of time, because you're eating into the useful time of the GPU, and you want that to happen as quickly as possible. But it can't be too quick, because as you'll soon see, that means the infrastructure requirements will go crazy. So you'll spend millions and millions of dollars and not really gain anything from it, okay? But let's go into that in a little more detail. This example, what I've said is, let's fix the amount of time you need to checkpoint, which is, say, 60 seconds. This, by the way, is fairly standard. NVIDIA recommends about 1 minute as if you checkpoint every hour. Let's pick a model. We've talked about GPT-3. Let's stick to that. 175 billion parameters. Checkpoint once an hour, 3,600 seconds. So far, easy, right? That's the famous parameter of 14 that I talked about. 2 for the model size and 12 because you're going to save 3 other sets of 4 outside that. And there are details that I've added in this from this paper here. Essentially, it's 14 bytes per parameter is what you would actually save. Now, what does that tell you immediately? It says, I have 14 bytes, I have 175 billion parameters, and each parameter is 14 bytes. Well, what's the size that I'm going to write out? I'm going to write out 2.45 terabytes of data as a checkpoint. Note that this doesn't depend on a whole bunch of stuff that many people feel it should depend on. Like, it does not depend on the amount of data that I'm going to train with. It does not depend on what kind of GPUs I'm going to train with. It does not depend on how many GPUs I'm going to train with. I could train this with an A100. I could train this with a B200, with the Blackwells. Doesn't matter. Checkpoint size depends only on one thing, which is the model size. Model size times 14 gives you exactly how much you're going to checkpoint, regardless of how long the run is, regardless of when you do the checkpoint, regardless of what GPUs you use or how many GPUs you use. None of that matters, okay? So now I have a size for the checkpoint. Now let's pick some sensible defaults for what tensor model parallel is and what pipeline parallel is. Now, I said 8 and 16. Where did I come up with that? The same publication I talked to you about, the one that's linked before, and this publication, this is from OpenAI, actually. Sorry, this is the famous publication from Megatron. They actually studied a large class of models all the way from 1.7 billion parameters to 1 trillion parameters, and worked out what optimal sizing you should have for this. In our case, our model is 175 billion. So if I look here, it's somewhere between 145 and 310 billion. So if I look across there, I could use 8x8 or 8x16 as tensor model parallel and pipeline parallel. I just picked 8x16 over here, right? Let's say we're training this with 1,000 GPUs. And what kind of GPUs? Well, these are actually H100 GPUs that I'm modeling over here. And the reason way I get there is I input in also the number of flops, the measured number of flops this thing can do, the number of petaflops per second that you actually measure. And good news is the same table also gives you how many petaflops per second they were able to measure. So 8 by 16 is 155, but note that this was for A100s. H100s are 3 times faster. So if you actually look at this table here, it's 155 times 3. That's how I get 465. Okay. So far, what have we covered? How to calculate model size after setting, you set the checkpoint time. And then you basically, the number of how you choose tensor model parallel and pipeline parallel, how many GPUs you use, what type of GPUs, how many flops there are. And the last bit here, or second last bit here, how much are you going to train on? GPT-3 was originally trained on 300 billion parameters. Okay, now we are at a point where we can train with much more data, and this is 1.5 trillion tokens that we're training with, or about 5 times as much. And the thing is that you can also now estimate how much computational power you will need. And it's actually very simple. And this is again from a beautiful publication from Kaplan et al. From OpenAI. And they estimate that it's 6 flops per parameter per token, which is required to process the data in a model of a given size. So you can calculate the total number of flops you need. You take 6 and you take the number of tokens, 1.5 trillion, and you multiply that by number of parameters, which is 175 billion. And that gives you the total amount of flops which is needed. And you can calculate that. And you say, okay, to train this model with this many tokens, I need 1.575 yottaflops. How much do I have available in exaflops per second? Well, we just calculated that. As that's how much I have, which is available over here with 1,000 GPUs, right? And now I can also calculate how big the total data set is, because remember I said 4 bytes per token, so 1.5 trillion, that's about 6 terabytes or so, okay? Everything on the left that we just talked about is completely dependent on purely the model and the mechanics of the LLM and the hardware that you're working with. On the right-hand side, now I can confidently do some calculations as to what this implies for infrastructure. First thing you've already looked at. Hey, this is 2.45 terabytes I'm going to write. But what does that mean? Because if I go to write 2.45 terabytes in 60 seconds, guess what I can calculate? I can calculate how much bandwidth I need over here. So I need a system that supports 40.8 gigabytes a second of write bandwidth to be able to successfully do this checkpoint, okay? How big is each of these checkpoint files? Well, I know the total amount that I need, and I know the total amount of GPUs in my pipeline parallel group, which is 8 times 16, not the 1,000. 128 GPUs, I can literally do some division. I say each checkpoint file is going to be 19 gigabytes in size, and there's going to be 128 of them, adding up to about 2.45 terabytes or so, okay? This immediately lets me also calculate how much bandwidth I need per GPU. This particular case is 300 megabytes a second. And it also, now because I'm checkpointing once an hour, I'm going to do 24 checkpoints an hour. And here's a very interesting and surprising fact, that you actually do need a fair amount of storage to be able to save these checkpoints. 24 times a day, you're going to write 2.45 terabytes. That means you're going to need a total of about 60 terabytes of space. Now, you'll see how this changes dramatically if I do things like changing the checkpoint frequency or something like that. Let's say instead of checkpointing once an hour, I say I want to checkpoint, say, every 15 minutes or 900 seconds, all right? Still using 60 as the checkpoint. Note what doesn't change. The checkpoint bandwidth doesn't change because I'm still writing the same amount of data, and I still have to do it in only 60 seconds. But now I'm doing 96 checkpoints a day. So I now need 235 terabytes a day. If I actually didn't get rid of any checkpoints and kept all the checkpoints, that would be like staggering 9.2 petabytes of storage I'd need just to train this job. Most people don't do this, to be perfectly fair. Okay, they will keep checkpoints for 3, 4, or 5 days, and then they will purge the rest. Or they may preserve checkpoints once a day or something like that, just so they have a point to go back to. and then purge the rest. Not that much different from what you would do with backups. Incrementals and fulls every once in a while, and then you only preserve some states at the end. So how you do this is totally dependent on you, but that's what you do, okay? So let's get back here to 3600 over here. And you'll see now that now you can also quickly estimate how much time this is going to take to train. Why? Because I know how many flops I need, 1.575, and I know how many flops I have, for 0.465 with 1,000 GPUs. Divide the two, convert that to days, and voila. And I essentially get, how long will it take? This particular training run is going to take 39 days. So in essence, what I'm giving to you is a very precise and tested model, which, given the input parameters for a large language model training, is able to predict exactly what you would need from the infrastructure side over here, okay? I told you earlier, there is no free lunch. Checkpoint is synchronous, and it's going to cost you something. What is it going to cost me? Well, if I look at how much impact there is on wall clock time, I'm essentially, what I see is, hey, 60 seconds divided by 3,600. That's the amount of time every hour that I'm doing checkpointing and therefore not doing training. That's about 1.67% of your GPU time that you're giving up for checkpointing. Now, it is tempting to say, oh my God, why that much? I'm wasting that much time. Let me checkpoint really, really aggressively, okay? So it's like, all right, let's say we checkpoint every 15, only give 15 seconds to checkpoint here. Sure, you do cut your ratio down to 0.42. Now you're only wasting 0.5% of your time. However, now you're building a system which has to support 165 gigabytes a second. These are expensive systems. They're not easy. And but note that nothing else really changes. Checkpoint size remains the same. The bandwidth per GPU changes because you're trying to do a hell of a lot more in a lot less time. And doesn't change any of the other parameters. So while you've saved money, there's a trade-off that you need to get much beefier hardware to be able to do this. This is why people don't go crazy saying, I want to do super tiny checkpoints, super small checkpoints at all. Well, there are people that do that because, one of the interesting observations is I've talked to people who run real hyperscalers. They run jobs with, 10,000 GPUs. And they say the failure rates are so high that it's not even worth actually doing training by doing external storage-based checkpointing, because we fail all the time. We'd be constantly restoring with that many GPUs because the failure rates are too high. So what they do is they do memory-based checkpointing. And in fact, my colleague from Microsoft, Glenn Lockwood, talked a lot about that in our talk at ISC, is that they do memory-based checkpointing, and those can be very fast, and the restores can be very fast. So you don't have to interrupt processing of the job just because you had some kind of failure. Most failures, they can recover very easily. So instead of having a very high number of failures, this starts to become a lot easier. So let me illustrate that. So I've actually done some interesting calculations using some mathematical methods like Poisson statistics to calculate what expected failure rates would be, okay? Generally speaking, experimentally observed rates are around 0.4 GPUs per day for every, 0.4 failures a day for every 1,000 GPUs. So for 1,000 GPUs, okay, I have a failure roughly once every 2 days, okay? Now, this becomes quite a bit more dramatic if I say, let me go to 10,000 GPUs, right? If I say 10,000 GPUs with this kind of failure rate, I mean, I would get a lot more failures as you do. Now, your run gets smaller, gets much faster. Now I'm running it in 3.9 days, but you still have 16 failures in that 3.9 days. And that's a lot of time which you actually would spend in doing recovery. This is why beyond a certain time, a number of GPUs, let's say about 4,000 or 5,000, it's worth looking at other ways to be able to checkpoint other than going to the very, very large systems like that. This gets aggravated even more if I start to increase the size of my model. So let's say I have a trillion parameter model over 10,000 GPUs. This one takes around 22 days to train, but I'm going to have 90 failures when this is happening. And I could do this run 1,000 times, and chances of me having one with no failures is almost zero. Okay. So I'll wind down at this point and open up for discussion and questions. But just to summarize what I've taken you through, okay? First off, why do we need to checkpoint? We need to checkpoint because inevitably hardware fails, or we need to retrace our steps and we don't want to throw out work. These large language models take a long time to train, and there's no sense in repeating the work, and therefore you want a quick recovery point. The intense bit about checkpointing large language models is they are large, and therefore the checkpoints are very, very IO intensive over here. Then I've given you a simple mathematical model. Hopefully everything I said made sense to you, but otherwise please do ask questions about it, where given only the parameters that I need for running the model, such as how long I want to spend checkpointing, how big the model is, how often I want to checkpoint, how I want to split up this model from a tensor parallel or pipeline parallel perspective, how many GPUs, type of GPUs, and how many tokens I want to train on. Just based on this, I can predict in entirety what the life cycle of the training would be. Everything from how big my checkpoint size is, to how much checkpoint bandwidth I would need, to how big each checkpoint file is, down to how long the job is going to take, how many failures I would have, et cetera, et cetera. And if you really wanted to, I put in a few financial metrics too, so you can figure out, hey, if it's $4 a GPU hour, then, oh boy, I'll be spending $21 million in being able to train this just on the cost of the GPUs alone. All right, so these are good tools to get a feel for how to approach something. So if your end user community or a data scientist come and say, I want to do X, and I need capacity for that. And now this gives a way for you to have a meaningful conversation with them saying, tell me more. How big is your model? How many GPUs are going to use? How many tokens are you going to train on? What kind of parallelism are you going to use? And based on that, now you can sensibly design a system which makes sense for your budget as well as the business requirements over here, right? So left to them, I've noticed that a lot of data scientists, and hopefully there are some around you, so this is not meant to be an insult, a lot of them seem to be unaware of what happens on the infrastructure side. So they will make crazy statements like, well, I need to checkpoint every 5 seconds. And it's easy. You say, all right, you want to checkpoint every 5 seconds? Well, guess what? You need a system with 2.8 terabytes write bandwidth per second. 2.8 terabytes. That's more than some of the largest supercomputers in the world have, okay? Even at 10,000 GPUs. So at that point, people start to look and say, oh, maybe that was a bit silly. Maybe I should go with 50 seconds instead of 5 seconds. And that now it's a lot more reasonable, even for a very large model over here. So it gives you a way and a method to be able to communicate with the data science community, gives you a way to understand the dynamics of what happens when training occurs and what you should expect from an infrastructure standpoint, and gives you some idea of how to extrapolate how long it will take and its dependence in the amount of data, et cetera, right? So if I double the number of tokens, for example, and I said, let's go with 3 trillion tokens, I will exactly double the amount of training time I need, because that's really what this thing really depends on. So none of this math for checkpointing, for size and impact, et cetera, is dependent on anything but the size of the model. But the rest of it obviously depends on what kind of hardware you have and how much data you're actually training on. So I'm at 10:45 on the dot, and I promised Boone that I'm going to pause now and open up for questions and comments over here. So let me stop sharing here so I can maybe look at a few faces as well and open up for any kind of questions.
Awesome. Well, great timing because we got a lot of great questions coming in.
Okay, great.
First one, this is from an anonymous attendee. This is in reference to the Alibaba paper.
Yeah.
We're asking, why would they get so many NV-link errors? We may just need to point back to the paper, but just curious if you had a take on that, Kartik.
So yeah, NV-link errors can occur for a variety of reasons. And honestly, this is because it's NVIDIA's hardware. I don't necessarily want to sit and diagnose a cause for it. But suffice it to say that the large-scale GPU systems are extremely complex, okay? They have a PCI switch complex in them. They have a fully proprietary NVLink network in them, in addition to external NICs and RDMA traffic between the GPUs themselves. There are many moving parts to something like this. So there is absolutely a full possibility that you could have errors from any of the subsystems which are connected with this. This may not even be connected with any of the hardware. It could be connected with some of the drivers which are there in the system. So if anything can fail, Murphy's Law rules. It will. So that's really what we're seeing here much more than anything else. But it's not just NVLink errors, nickel errors, CUDA errors, ECC errors. Some are server side, some are GPU side, some are just timeouts. Things just pause and hang. Those are still counted as outages for Alibaba.
Another question here from Steve.
Yeah.
In the cell that you were referencing, how does checkpoint size react when the client cluster is smaller, such as 64, 128, or 256 GPU? And then they're asking, is the Excel more for 1,000 GPUs and up?
So the answer to that is absolutely no dependence at all on anything else. And no, this Excel is for any number of GPUs you want, okay? I moved this to 10,000. Let's look at, say, like twice the number of GPUs, okay? Note that the size of the model is what determines the size of the checkpoint, nothing else. I can change the number of GPUs. I can change the number of tokens from 3 trillion to 5 trillion. I can change the pipeline parallelism as well. Let's say I'm doing 2048 GPUs over here. Let's look and see. That could be an 8 by 35 configuration. A 1 trillion model actually will be 8 by 64. So let's make this 64. I can change any parameter I want. What doesn't change is how much I want a checkpoint. And the checkpoint size remains absolutely constant regardless of what you do. And thanks for the question. Very important question, because many, many people think that if I change the number of GPUs, I'm going to need much more, checkpoint bandwidth. Absolutely, totally, completely false. Okay, if anybody ever tells you that, listen very carefully to everything else they tell you, because they're probably lying to you about other things too. It is absolutely not true. Okay, checkpoint size only depends on the model size, not on the number of GPUs, not on the type of GPUs. So I've had people come to me and say, "Oh, we are looking at running 1,000 Blackwell GPUs. I must need much more storage, right? And much more bandwidth, right?" I'm like, no. All depends on what model you're training, and that's the only thing that will decide this. It is not dependent on the data. It doesn't depend on how long it runs. It doesn't depend on the GPUs. Does that answer your question, Steve?
I think so. We got a few questions here from Frank and from Darren about power and cooling and heat generated. Well, Darren had a comment. He was wondering, if he said it would be interesting to see if, like, if this table could include power and cooling required to run a given model. And then Frank also asked a similar question about, saying something to the tune of the amount of heat generated is unsustainable, and from what I can see, not getting any better or worse. I don't know if you have a take on this. He's asking if there's any light at the end of the tunnel from a heat generation perspective.
Oh yeah, 100% agree, guys. These are enormously power hungry systems. Okay, so if I look at, say, H100 class HGX or DGX system, the average power draw for an 8 GPU system is 10.4 kilowatts. That's massive. Okay, and now if I want to say run 4 of these in a rack, I need a rack which is about 45 to 50 kilowatts in a rack. Most data centers for enterprise have 8 kilowatt racks, 10 kilowatt racks, 15 kilowatt racks on a good day. Almost nobody has 40 kilowatt racks. The next generation of the Blackwells, especially the MGX versions, the NVL72s from NVIDIA, have like a 120 kilowatt rack requirement, 120 kilowatts. So you can imagine, if you're taking in that much power, you're going to put it out as heat. So these get hot very soon, and they are power hungry beyond belief. And typically you add about 20% more on the cost for networking and cabling. Cabling, I've seen installations that we've done where the cabling is in 10 kilometers of cable just to support 1,280 GPUs. It's massive. It's really, really massive, all InfiniBand networking. So yeah, absolutely, we can calculate out that thing, but it's frankly simple math. It's just take the number of GPUs and, And remember, 8 GPUs is 10.4 kilowatts for the H100s. It's closer to 14.5 kilowatts for the Blackwells. And then you have your number. It's just simple math. Okay. And the whatever comes in must go out, therefore the rest is heat. So this has resulted in a lot of interesting strategies people are looking at, right? So the Blackwells, for example, you cannot do this in air-cooled racks. When you go over 50 kilowatts, you're going to go to liquid cooling at that point. In fact, 120 kilowatt racks that are commercially out there are all liquid cooled, okay? Many people, and this is not yet true for the Blackwell because it's not shipping, are absolutely looking at immersion cooling. I have many customers who have immersion cooled systems at this point where they essentially dunk the entire server in a bath of mineral water, in like a bath of mineral oil. And that clearly significantly reduces any fan noise and all that, but it also dissipates heat a lot more efficiently and it cools the system a lot better over there. But, it's mineral oil, so it's kind of icky, there's lots of liquid out there, so not everybody is a huge fan, but it certainly is a way to manage the thermals connected with the kind of things that we're looking at. But the next generation NVIDIA GPUs, guys, let's just face it, you're going to have to go to liquid cooled racks. Most enterprises won't be able to do it, which is why we do anticipate that a lot of those kind of workloads will probably be run on either the hyperscalers or tier 2 AI cloud service providers who are specialists in GPU type infrastructures. Those data center providers are absolutely building out this sort of infrastructure for power. So hopefully that helps.
Another question here from Adil. Does checkpointing improve dramatically with using NVMe-based storage versus SAS or SATA drives?
I would say that I don't even think SAS or SATA drives is an option in something like this, unless you're doing memory-based checkpointing, okay? If you do memory-based checkpointing or local checkpointing on the GPU server itself, which can also be done, that local checkpointing is always NVMe, never SAS or SATA. And memory, of course, doesn't touch the external storage systems. External storage systems in this field, in generative AI, are 100% solid-state systems, okay? Especially when you're doing things like checkpointing to external storage. If you're checkpointing to memory, that external storage system could be something else because you're not really, there's nothing in the synchronous data path that's actually going to storage. It just needs to be fast enough to be able to bleed off the checkpoints from local NVMe as it comes in, and that can happen asynchronously at a lot lower frequency. But almost always, for example, if you look at the list of all the vendors qualified for NVIDIA base pod or super pod, these lists are public. 100% of them only have been certified on all solid-state storage systems. So be very, very, very cautious before you think that you can pull this off on a SAS or SATA-based system over here. Chances are very high that you will run into serious I/O bottlenecks, either through training or through data preparation or through inference if you're doing that. I've seen, we work with hundreds of customers, haven't seen a single one use solid state or anything but solid state for external storage. Okay?
Perfect. Well, that is all the questions that we have time for today, Kartik. Thank you.
Okay, excellent. Guys, super happy to see you all. I'm going to basically go to a few wrap-up slides to Boone. We've already gone through asking questions. Thank you very much. Great questions, guys. That's excellent. And I will let Boone take us out with the final slide over here.
Awesome.
Go ahead.
Thanks everyone for joining. Thank you so much, Kartik, for speaking. Like I mentioned, the recording of this webinar will be sent out to you at the close of the event. But if you want to learn more, if you want to learn more about, today was not all about VAST, but if you want to learn more about VAST, we do have a bi-weekly live demo. So if you have questions that you wanted to get answered today, or if you just want to learn more, you can scan the QR code on your screen here, or you can go to vastdata.com/demo to join us for one of our weekly live demos that are every Tuesday and Thursday. But with that, I think we'll close it out for today. Thank you so much, everyone. All
righty. Well, thank you all, folks, and hope to see you again. And happy to go on other adventures with you on this topic. Thanks.